record. Okay. So I will take one example. Can you open your maybe Excel file or something? You consider a motor, 200 kilowatt motor. Please write down. Let the motor rating be 200 kilowatt. Okay. Please write down motor is 200 kilowatt and the fan moment of inertia you please write down, which is Jm. Okay, Jm is 1200 kg meter square, and the load that is sorry, the fan is Jl. Okay, fan is Jl 1200. Motor is Jm, that is 11 kg meter square. Okay, so Jm plus Jl is how much? 1211. Okay, now let me go to this equation. Basically, what see, I will divide my speed torque curve into 5 different speed. The RPM here is actually 991 RPM. Okay, for this motor. Now let me divide it to 1, 2, 3, 4, 5. 5 different RPM. 5 steps. So 0 to 198 RPM, 198 to 396, 396 to 594, 594 to 792, 792 to 991. So I have divided my speed torque, this one, to 5 intervals. Okay. Now the basic equation, okay, for delta T. Delta T is 2 pi by 60 J delta N divided by the difference of the torque. So here 2 pi by 60 is here. What is J total? We know J total is 1211 kg meter square. Okay. And what is delta N? Delta N is the change in the speed. Okay, so the change in the speed is given here. It is all 198 RPM. Then what is this del Tn minus T load is the accelerating torque. The difference of the motor torque minus the load torque. Okay. So this motor minus load torque, what is the total torque? Total torque is 11927. Okay. How do I determine the torque? In the last class, I told you torque T is equal to P is equal to 2 pi nt. So P divided by 2 pi n will give you the torque. But in the last class, you have done it. So you know the torque is 1927. Now this one, no? See the difference of the torque. What happened? The difference of the torque, input minus output, we can, something like that. Okay. So that torque is like a percentage. So initially I can say 99%, then 92%, then 78, 57, 29%. See, when you are doing this manual method of, okay, what you can do is you can take these percentages 99, 92, 78, 57, and 29. You can take this, okay. But if you are if you don't want to do like this, there is one more method. That method is you actually, instead of you integrate this equation. If you know Fortran or Python or any software, you can or MATLAB, you can integrate this equation in the software, and you can exactly determine the time. Okay, instead of this method also.
So how did you get those how did you get the 0.99, 0.92? Those are assumed values, right?
Okay, that's what I'm explaining. What I see, the initially the difference. See, there are five instances, right? There are five instances. Initially, the difference in the speed. See, what is the difference of the motor torque and the load torque? This is assumed by our ABB guideline. What they have, why they have made the assumption, I will tell you. Initially, see how till when will the motor, or I will put back a question to you. When the motor is running, what is the accelerating torque, Mr. Pinaki?
Zero.
Zero.
If
That is,
it's absolute, if it's running speed, it's zero.
so basically the motor should not accelerate. When it is running, it is running. So there is no
It is running,
accelerating
it's
torque.
running. It's zero.
Yeah.
Accelerating torque is zero.
So basically Tm minus TL will be zero. Ta is equal to zero. So here you see, basically when the motor is starting, the accelerating torque is high. That's why he has taken 99%. So as it accelerates 92, 78, 57, finally when the motor is in the fifth stage, he has taken 29%. So basically these are assumed values. 99, 92, 78, 57, 29 is assumed values. Is it clear?
Yes, sir. So then
Uh,
1211 is from adding the inertias. 198.2 is the value that we get. Can you come back to the previous equation, sir?
it
Sorry.
see,
198.2 is
I will tell you. See here, the totals. What is the total RPM? What is the RPM of this motor?
991.
It is 99991, right? The
Yeah.
RPM of the motor is 991. So 991 divided by 5 is how much?
991 divided by pi. Uh, 315, sir.
991 divided by 5 is. Please check once again.
991 divided by
5, 5.
pi, right?
Yeah.
5. Sorry,
5,
sorry. You said
5,
5.
5.
5. Excuse me. 198.2, sir.
Yeah. So here basically taken the motor RPM, divided it by 5 to get this 991. Okay. So, so you are clear about this 198.2, no?
That's because he's taken 5 slots. He's taken five ranges.
Yes, because this is delta n. Delta n is what? Basically from 0 to 198, delta n is 198. 198 to 396, delta n is again 198.
Okay. That is taken.
Clear?
Okay, sir. Yeah, now it's clear, sir.
So basically, then you determine the time. What is the time required for the motor to go from 0 to 198 RPM? 13 seconds. Then the motor has to go from 198 RPM to 396 RPM. It will take 14.3 seconds. Then from 396 RPM to 594 RPM, it will take 16.7 seconds. From 594 to 792, it will take 22 seconds. From 792 to 991, it will take 45 seconds. So from 0 to 991 RPM, the motor total time, you add all this, it takes 112 seconds. Is this clear?
Yes, sir.
I have a small exercise for all of you. You please take this data sheet. I will share one data sheet in the WhatsApp group. Okay. You all, can you do that this one? Motor, similar calculation you can do. Maybe you can do it. You will do it later. Okay, not now, but I will share it. I will share. Anybody of you having any motor data sheet with speed, torque, all those things? Pinaki, you are having any motor data
Not
sheet?
right now, sir.
Speed,
No,
torque,
sir.
all.
Don't have, sir. Not right.
Okay, okay. Then I'll do one thing. I will share one ABB data sheet. I have shared one ABB data sheet in the WhatsApp group. Okay, please. Today you calculate the starting time. Okay. Did you get the? Okay. Are you able to see the screen now?
Yes, sir.
Okay. We'll go. So we calculated the starting time. We got 112 seconds. Similarly, I've given you one exercise. Please do that exercise today. Tomorrow, any doubts are there with that exercise, we will discuss. Okay. Okay. Now, any doubt? Why, Mr. Hold on. Let me stop the share. Why, Mr. One of our friend dropped down. Okay. Mr. Inamul, any doubts on the motor starting phenomena? Mr. Inamul, Mr. Lognathan,
I'm clear, sir, I think.
any doubts in the motor starting phenomena and how to do the calculation?
It's fine, sir.
Okay. Mr. Pinaki, any doubts in the motor
No,
starting?
sir. No doubt, sir.
Naveen Kumar,
Sir, all clear, sir.
clear. Vijay Renuji,
It's clear, sir.
okay, okay. So, I basically explained you the motor starting phenomena number one. Number two, the speed torque curve, the curve load curve, then the accelerating torque, then the basic equation. Okay, now you please, and I've given you one how to determine the speed, how to determine the starting time. Okay, so I have given you an exercise also. Please go through that exercise. Please determine the starting time. So tomorrow you have to tell me what is the starting time for that motor. Okay. See, if you want, if I determine the starting time, see, I will let me go back here. See, if I determine the starting time with this method, I will only get that time. But if you want to get an exact curve, you can do integration also. But I will not go to that integration. Okay. Now let me move to this inrush of a transformer. Okay. Okay. Before I go to let me explain you about the phenomenon of inrush. See, if you go to the equivalent circuit of the transformer, I have my primary winding, I have my second. Okay. Then I have my leakage, reactance, all those things. Okay. Now, see, what is your transformer made of basically? Transformer is basically made of what? It is nothing but basically it is iron, and then I have my windings, right? And then I have my winding. So transformer is basically made of iron and winding, right? Now I have my primary winding here. Above that, I have my uh, secondary winding, right? I have primary, I have secondary. Now, what happens in a transformer? Current basically flow to the primary winding, and from primary to secondary via the air magnetic field, energy is transferred, and then the energy comes out from the secondary winding. Now, before this is all what happens in the normal condition. But when in the starting, okay, in the beginning, the moment the current flows, what happens? See, current has to flow. So, see, from this primary winding to the secondary winding, energy has to flow, right? So, where does it flow? It flows in the air. So, in that air, a magnetic field has to be set up, right? So in order to set up the magnetic field, some energy is required. So as soon as you turn on a transformer, the first thing that happens is setting up of the magnetic field. Okay, to set up that magnetic field, some energy is required. Now that energy is basically your magnetizing current. Okay, magnetizing current. Now that magnetizing current is what leads to inrush current. Why inrush? Because see what happens, as soon as you start this magnetizing current will go there, this inrush current will go. So this will basically this circuit. In the beginning, what happens? The impedance offered by this will be very less. Gradually, when current starts flowing, it will, after the magnetic field is set up, the current here will normalize. So initially, you can see in your transformer, let's say 1 MVA transformer. 1 MVA transformer, let's say 11 kV. 11 kV transformer will be 55 amps, right? 55 amps. So the normally, what is your magnetizing current? Pinaki?
Almost it will be 30 times or something like that for a transformer.
Normally, what is the magnetizing current? Normally.
It's the no load current, sir, right, sir?
Yeah, no load current. How
No
much?
load current would be maybe 1% of your load current, sir.
1%, 5%, how much?
Some 1% or something like that of your full load current.
1%. Mr.
Yes, sir.
Anybody else want to tell what any typical figure for the current, no load current? Mr. Vijay. Mr. Vijay.
Around 3 to 5%.
3 to 5. Okay, Mr. Inamul, any your data sheet? What is the no load current? Okay, let me take. Yes, sir.
Less than 1 to 3%.
Okay. Now let me suppose if I take 1, 3, 5%. Suppose 1% means
3%, sir.
okay, sir. 5.5. 1% means 0.55 amps. 3% means
For a small transformer, it should be less than 1%.
okay. It will 1.65 amps. 10% to 5.5, 2.75 amps. Okay. So we will see. Let's say approximately for this transformer, let's say anybody having data sheet of a 1 MVA transformer, 7 bar 415 volt, the no load current values, please share in the group 1 MVA transformer. So basically the start now, the magnetizing current here will be 2 amps approximately. Okay, so here it will be 2 amps, right? Out of 55 amps, 53 amps will flow here, 2 amps will flow here, right? But now during starting, what happens? The impedance of this path will be very less. Because the impedance here is very less, this will draw how much? Around 9 times, 10 times, 12 times, something like that. So it will draw around 600 amps. This path will draw around 600 amps. So you can see the starting current in a transformer is almost like 600 amps. And you can see that this current reduces to almost 2 amps. So 600 amps to 2 amps, so now less than 1%. Because you can see the transformer also, you can see something like this. Not like that. I have to draw time versus this one, no? Time. So current versus time. But okay, this curve, see, one thing you have to remember in a motor, the starting time of the motor, Mr. Pinaki, how long does the transformer take the inrush current? How long? Any idea?
Just a few seconds, sir. Just like maybe just few microseconds only.
Okay. Time versus current. I will draw for this. Let's say this is the motor, right? Motor.
Yeah.
Now, transformer, the starting current will be much higher. So to be somewhere here. But the time taken to start is how much? It will be very less. 100 millisecond. How much? 100 millisecond.
I was under the impression it was in microsecond, okay, but millisecond.
0.1 second, 0.1 or 0.2 second. Some 4-5 cycles. See, microsecond is very, very less. Microsecond is very less. It will take 4-5 cycles, whereas your motor is taking 10, 20, 30 seconds. Okay. So if I want to draw that here, can get it like this. It will be like this. Starting current will be high. The time will be very less. Okay. Starting time for a transformer, remember, is very less, something like 100 millisecond. I will first thing, don't use the word starting. In transformer, they don't use the word starting. They use the word inrush current. Inrush current. They will not use the word starting current. Okay. Or a energization, magnetic. There is one more term they will use, energization. They will use the term magnetization. Different terms are there, but they are not using the term starting current. Okay. So now, uh, everybody clear on the phenomenon, why transformer there is a inrush during the
So
energization.
just to sum up, sir. So
Yeah,
just one clarification, sir. In the
yeah.
inrush, when the inrush is happening, the magnetizing circuit that gets short circuited, right? That's why we are having such a high magnetization, right?
Not short circuit completely. You are correct, but not complete short circuit because then it will become infinite current. Instead of short circuit, it will be very, very less.
Very less impedance. That is what is causing the such a high inrush of about 10 times the current.
Correct, correct. Basically, yes, you are
It is 10
absolutely.
times of the full load current of the transformer, sir, or 10 times of the magnetizing current of the transformer.
It is 10 times of the full load of the transformer. That's why
Okay.
I
Yeah.
I want you people to actually go through, share. See, if you have any test report, see, type test report. If you have gone through any type test report, please share it only with that
Yes,
particular
sir.
sheet. Okay, then we can
Yes,
go
sir.
through it.
So in that T versus I curve, for the
Yeah.
M, you have written M. So the bottom curve is the transformer,
Yes, you are correct. This is
but then
the.
current will be much lower, no, sir. 100 milliseconds means it will be almost hugging the line, no, hugging the. It will be almost invisible compared to the motor, no, sir. The time.
This current, see, this time will be 100 millisecond. Now this time
And
is,
if
let's
above
say,
that the time is
10 second. Now this current is 6 times. This current is 10 times. Okay. Any doubt on that?
no, sir. It's okay.
Okay. Okay. So, clear up to this one? Okay. Now, go back to. Okay. See, last class actually we have missed. No? I will cover up by doing, little extra classes in the next class. Okay. Is that okay?
Yes, sir.
Yeah. And now for today, I think I'll wind up today. It is almost 8:10. Tomorrow I will be covering these types of the curves. Okay. IEC
Okay,
curve,
sir.
then this IEEE curve, and all these curves will be covering. And on coordination margin, those things we will cover. Okay. And please, I have given you an exercise today. Without fail, please do that exercise. Okay.
Yes, sir. Sir, in that exercise, sir, I just went through the data sheet. There are some
Yeah.
data details which are not given. The inertia of the load is not given. The torque, both the torque value, both the torque and the of the motor and the torque of the load are identical, sir.
See,
Is it?
actually, the torque of the motor load will not be there in the motor data sheet, right?
It's mentioned. Okay, sir. It's mentioned, sir. Actually, torque of the load is mentioned. Actually.
Uh, you can take whatever is given there. Actually, the torque of the load normally will be very, very high compared to the torque of the motor. It will be very high. Okay.
Okay, sir.
I actually I'm not having this load. Getting the torque of the load only is a headache. Motor torque you will get. The torque of the load is difficult. If I get some other example, I will surely share. Okay.
Yes, sir.
Yeah. So any other examples, if you get also, you can share. We will do it. If any one of you are having the torque equation of the